Swayam Prabha. Digital India. Educated India.
Now, what we have done in the last lecture is as follows. We discussed in the beginning who first proposed and developed the electron beam machining process and machine. That gentleman patented it, developed the EBMM machine somewhere in the year 1952. Then he made so many changes and used it for electron beam welding purposes also. Then power density of different thermal manufacturing processes we had discussed in the last class, especially electric discharge, micromachining, laser beam, micromachining, electron beam, micromachining. So, highest in density, if you recollect, was in electric discharge micromachining. Then we discussed the basic elements details of electron beam machining machine. Then after discussing different basic elements with the help of the schematic diagrams, we discussed why do you need vacuum in the electron beam micromachining chamber, because if you are not using the vacuum, then in some cases you may not get any machining done, or if you get machining done, then it will not be as per the quality requirement. Then we discussed various types of electrons gun, focusing system, electromagnetic lenses we are discussed. Then electron beam generator was shown over there, control system and workpiece chamber. And workpiece chamber you have various facilities, so that you can see what is going on the workpiece being machined. Now, we are going to discuss various issues related to micromachining. What are the characteristics of electron beam machining process? We have seen the cavity formation, penetration depth, both are very important, and then thermal and physical properties of the workpiece material are going to affect the performance of the process. So, we will see these properties. Then characteristics of electron beam. Now, surface interaction, the interaction between the workpiece material and the electron beam. So, the kinetic energy of the electrons is converted into thermal energy of extremely high density. Now, the energy is very high, so that it is able to melt the workpiece surface, and not only melting, but vaporization also takes place. And the major mechanism of material removal is by vaporization. First melting takes place, and then the material gets vaporized and then goes out of the cavity. Material removal should take place before any substantial percentage of the heat absorbed or heat is transferred into the bulk material. So, the intensity of the heat is very high, then before really the heat transfer takes place to the bulk material, the material may get evaporated, and that evaporated material can be removed from the workpiece. Because temperature is very high in electron beam micromachining and electron beam machining. So, there is a certain substrate of the workpiece below the area being machined. The metallurgical properties of that material substrate changes, and that is known as heat affected zone, and there is a damage to the workpiece also because of micro cracks and other things. And also, as I mentioned in the last class, you may get the recast layer formation, that molten material gets redeposited on the machine workpiece surface, and that recast layer should always be removed before you are going to use that particular product. Then you one of them important characteristics of the process is efficiency of the EBM, electron beam machining, and rate of transfer of energy into the workpiece material also is an important parameter which decides the efficiency of the EBM process, and rate of removal of molten vaporized material is very important aspect of the EBMM, electron beam micromachining, because material may melt and it may get redeposited if it is not removed by vaporization or otherwise, so that the efficiency will go down if it is getting redeposited, resolidified and then redeposited on the machine workpiece surface. So, that this is going to affect finally the efficiency of the electron beam machining process. Cutting speed, it is recommended to scan the beam rapidly on the workpiece surface across the surface to be machined. Otherwise, you may get the fissure which may be deeper than what you want, or it may not have the characteristics which you are looking for in the machine workpiece. So, it is also needed to minimize the thermal diffusion problem, to obtain narrow width of cutting track that we have seen earlier also, and the controlled dimension of the machine object, because if thermal diffusion is taking place, then you may end up with the heat affected zone as the larger heat affected zone, which is not desirable. And we are always interested in the minimum width of cutting. Suppose you are making the cavity, then this is the width of cut, and if this is larger than what you want, then it will not serve your purpose. So, scanning speed should be carefully optimized, so that you get the proper width, and this is the depth, proper width and the depth of the cavity, they are controlled by the scanning speed. And definitely the, as mentioned here, the dimensions of the machine object are also controlled by the scanning or scanning speed of the beam. So, it should be optimized. Now, you can see here, this is the thermal diffusion. So, we want to minimize the thermal diffusion width, and that is what is given here in the first point, that scanning speed should be controlled, optimized, and rapidly does not mean that you do not get the proper width of the cut. So, rapidly here simply means that you should optimize the surface scanning speed on the workpiece surface, so that you do not have these three problems over there. You can clearly see this is the width of cut, depending upon the speed you are going to get this thermal diffusion layer or heat affected zone, which is really not desirable, but depending upon the scanning speed you may get it, depending upon the scanning speed and the energy per pulse. So, this is the ideal one, and this has been taken from this particular paper. Now, conduction losses, principal cause of loss of efficiency in the heating process, because if there is a large on time of the pulses, then heat may get diffused into the workpiece, and you will have the conduction of the heat into the bulk material of the workpiece, and efficiency will go down. It is advantageous to work with as small a beam as possible. Small means the diameter of the beam should be as small as possible in order to minimize conduction losses. So, for minimizing the conduction losses, beam diameter selected should be small enough. The temperature is directly proportional to the beam power, right. So, if temperature is very high because of high beam power, then other problems will arise. Inversely proportional to the beam diameter, if diameter of the beam is larger, power remains the same, then temperature will be different. It is directly proportional, the temperature will be different, or it is inversely proportional to the beam diameter, because if larger the diameter, then in larger area the energy will get distributed and you will get the lower temperature as compared to the smaller beam diameter. An increased spot size will lead to an increased beam power is necessary for the same heat intensity. If increased spot size is there, that means beam diameter is larger, then you need the larger power in that particular electron beam, so that you get the same heat intensity. If the beam diameter is increased and you are not changing the beam power, then definitely the intensity will reduce. Coarse machining with a rapid rate of material removal is possible. If you are not interested in very fine cut or very fine features of the workpiece, then you can have the rapid rate of you can have the coarse machining with the higher scanning speed, and you will have rapid rate of material removal. Then there is a heat affected zone, as I have already mentioned to you, HAZ. It is abbreviated as HAZ. The heat affected zone depends on the energy of the incident electrons or the current of the beam. Because larger the energy, definitely you are going to get larger heat affected zone. So, the energy of the beam should be optimized, so that you get minimum heat affected zone. The diameter and distribution of the beam on the focused spot, the nature of the target material is very important, or the workpiece material is very important, which governs the heat affected zone. Because if thermal diffusivity and thermal conductivity are high of the workpiece material, then you are going to get higher heat affected zone. You may get different heat affected zone for different diffusivity and different conductivity of the workpiece. The rate of growth of heat affected zone is governed by the diffusivity and conductivity of the workpiece material. The final dimension of heat affected zone are again governed by diffusivity and thermal conductivity of the workpiece material. Then melting and vaporization temperature of the workpiece are also going to govern the material removal rate, because larger the melting temperature and vaporization temperature, then definitely smaller will be the material removal rate, if energy input remains the same. Then hardness after machining, highest at the entry into the hole and lowest at the exit of the hole. So, hardness of the workpiece material may get changed after machining is over. Pulse beam operation, appropriately biasing the cathode grade, reduction in conduction loss. The material at the focused spot can be heated to high temperature before any appreciable conduction of heat can take place. It should always be kept in mind that focusing, say this is the workpiece, then the focusing of the beam should be on the top surface of the workpiece, or I mean not only the top. Suppose you are machining here, machining is taking place here, then the focusing should be here, not here, not here at the top, wherever material is to be removed. So, the focusing of the beam should be at that particular surface to get the best results. High precision or reduction in spot fringe effects, mean rise in temperature of the workpiece is less, then low rate of absorption of energy by material at the spot, and low rate of propagation of temperature disturbances, and speed of the computer is also a critical factor, because here computer means control system, and control system is going to control, because all the operations, movement of the workpiece, beam diameter, beam focusing, beam location on the workpiece surface, etc. So, it should be quite high to control it before really anything get changed on the workpiece. Pulse modulation to expand the range of hole sizes and the shapes, modifying the beam intensity into a series of sub pulses for deeper penetration, because deeper penetration you can machine or drill the hole with higher aspect ratio, oscillating the focal length during the pulse time for better cylindricity, and oscillating the beam spot position to achieve not round holes like slots, ovals or triangles you can obtain by oscillating the beam spot position, if you are not interested in that particular hole or cylindrical hole of the size of the beam diameter. You can see here, this is a slotted hole. Now, when you are oscillating the beam like this, then you can get non-circular holes or the holes like this or cavity like this. So, by oscillating the beam you can get different cavities, whatever you like. You can get like this also, or you can get like this what you have made, or cylindrical, or any parabolic or different shapes can be obtained by oscillating the beam on the workpiece surface. So, all this should be done, or all this is done with the help of the computer. So, this has been taken from this particular reference. Now, maximum current density in the image is given by this. You can calculate the current I, and the maximum cathode current density J C is limited to about 2 ampere per centimeter square by the maximum temperature of about 2800 Kelvin. So, cathode temperature is around 2800 Kelvin. It is thus only possible to increase the current density of the beam by increasing the accelerating voltage V. The maximum value of V is limited by the expense and difficulty of the working with very high voltage, because as the voltage is increasing, the difficulty is increasing and the cost of the EBM machine also increases. In practice, the highest voltage used has been about 150 kilovolt, while for thin film machining the limit is about 60 kilovolt. So, depending upon the thickness of the workpiece, its properties and the feature that you are going to machine, you have to decide what should be the input voltage or what should be the voltage for this particular purpose. The maximum semi angle is limited by the spherical aberration of the object. This is the reference from where this particular equation has been taken. MRR due to vaporization can be calculated as follows: material removal rate is equal to the zeta into P over W. Now, here zeta is cutting efficiency or machining efficiency, P is the power in joules per second, and W is the specific energy joules per cubic centimeter required to vaporize the workpiece material. See, here the emphasis is being given to the vaporization of the workpiece material. So, what I want to say is that the main mechanism of material removal is vaporization. So, while calculating material removal rate, vaporization is taken into consideration. So, the workpiece material first gets melted and then only it gets vaporized, and specific energy can be calculated by this particular formula. Here is the specific energy you are using in this particular equation. So, this is nothing but W equal to C P C P S into T m minus T I plus C P L T V minus T m plus H f plus H v. Now, this is an important equation here. C P S, C P L, H f, H v, T m, they are the, and T v, they are the properties of the workpiece material. C p is the specific heat and S stands for solid, and here L stands for liquid. T m is the melting temperature, as you can see, T m minus T I, and T I is the initial temperature of the workpiece or the temperature in the machining chamber, and T v is the boiling temperature of the workpiece material. H f is the latent heat of fusion. When material is melting, then you have to account for this latent heat of fusion, and when it is evaporating, then H v is the latent heat of vaporization. So, C p is the specific heat as mentioned over here. Here substitute S, that is over here, and substitute L, that is over here, C p L. S stands for solid and L stands for liquid. So, with the help of these two simple equations, you can calculate material removal rate in case of electron beam micro machining as well as electron beam machining processes. However, you have to know in advance the efficiency zeta of cutting efficiency. P is the power you know already through the instrumentation of the machine setup, and W is known to you with the help of the properties of the workpiece material. So, you can easily calculate what is going to be or likely to be the material removal rate in a particular process. Now, let us see what are the characteristics of the holes drilled by electron beam micro machining or electron beam machining process. Now, please see it carefully. Now, these are the holes 0.1 millimeter, here this is 0.5 millimeter, 1 millimeter height, this is the 3 millimeter height which is expanded height, this is 5 millimeter and this is 8 millimeter. Now, you can see the shape and size of the hole. Here it is at the top it is a different shape, and then it is bell bottom kind of the shape, and finally again at the bottom exit side again the diameter is small one. So, specifically required forms can be obtained by optimizing the input parameters over a wide range. At the beam entry point, the drill hole normally features a slight rounding. You can clearly see here, this is the rounding of the input hole, top hole at the top. Here also there is a rounding, you can clearly see it. This is the rounding taking place at the entry side of the hole, and the edge at the beam exit point is always sharp and burr free. Now, you can see this is the exit side, this is the exit side, this is the exit side, and you can clearly see here that they are comparatively sharp and no burrs are formed, as we have seen in case of metal cutting processes. Say drilling is being done, burrs are being formed, milling is being done, burrs are formed. Even in turning cases, many times you find the burrs are there, but those kind of the burrs are not formed in case of electron beam micro machining and electron beam machining. So, this schematic diagram really gives a clear picture of the shape and the size of the hole that you are going to get. That you can see here, this is the rounded here at the top and largest diameter of the hole. In the middle it is the smallest diameter as shown over here, and at the bottom it is the sharp burr free but smallest diameter that you are going to get. It may be even smaller than the D which we can see in the middle of the hole, approximate middle of the hole. Now, one important thing that you have to note here is that you are not getting a straight sided hole, that is many times needed in case of straight sided hole, because such kind of the hole that you are going to get here in case of electron beam machining, that is like this, may not fulfill your purpose in many applications. So, you have to be very careful, because you are talking about the micro size of the hole. So, you may not be able to realize by the naked eye, but when you take the zoomed view of the cut section of the hole, then you will realize that oh, it is not really a straight sided hole, rather than it is a curved hole. So, you have to decide carefully whether it will serve your purpose or not, and especially when it is a deep hole or depth of the hole is large enough as 8 millimeter, 5 millimeter, such kind of the characteristics of the hole may or may not be acceptable to you. And this has been taken, these pictures have been taken from this particular website. You can see cross sectional view, I have already explained to you. These are the actual holes drilled in the chromium nickel steel, which are shown over here of different sizes. Round entry is there and sharp exit is there, which I have already explained. Now, capability of electron beam micromachining or electron beam machining. This process can create a hole with a single millisecond pulse of the electron beam, high hole making rates if the workpiece and beam move relative to each other. So, when you are making many holes, so you have to have the relative motion between the workpiece and the beam. It is the relative motion. So, it does not matter whether you are moving the beam or you are moving the workpiece with reference to the beam. For example, 100 micrometer diameter holes can be drilled in 300 micrometer thick sheet at 1500 to 2000 holes per second. So, you can see the capabilities that you can drill as many as 2000 holes per second in a sheet which may be around 300 micrometer thick, and the diameter of these each holes may be around 100 micrometer. So, it really tells you that it has very high capabilities and it can drill the holes at a very high rate. The time required to make a hole varies directly with the size of the hole and the thickness of the workpiece material. Definitely, here you are talking about the 300 micrometer, thickness of the workpiece may be much more than 300 micrometer or even smaller than 300 micrometer in terms of files. They can be smaller than 300 micrometer, or if we are talking of the sheets, then they may be larger, much larger than the 300 micrometer. So, that will decide whether it is 2000 holes per second or less than that or more than that. 20 holes per second when electron beam drilling 5 millimeter deep. So, you can see the difference, here it is 2000, it is 20, but the thickness of the sheet has increased from 300 micrometer to 5000 micrometer or 5 millimeter, and depth is and 0.7 millimeter diameter hole is there, while it is the 100 micron hole. That means, this is 700 micron, this is the 100 micron. So, you can see clearly that by changing the thickness of the sheet and by changing the diameter of the hole, the rate of drilling holes per second has gone down substantially, say from 2000 holes per second to 20 holes per second. Thus, in applications where the part requires tens of thousands or millions of tiny holes, the electron beam drilling process is hard to beat, because you will see many processes like electrochemical micromachining, electric discharge micromachining, laser beam micromachining and so on for drilling the holes, but it is really difficult to achieve this kind of the performance, that 2000 holes per second or 20 holes per second in 5 millimeter deep or 5 millimeter thick sheet is really difficult. So, under certain circumstances for certain applications, it is extremely good process, that is electron beam micromachining. The repeatability of the electron beam drilling process provides hole size accurate to plus minus 0.635 micrometer and location accuracy to 12.5 micrometer. Now, what are the various applications? I will give you an overview of different kinds of applications in different fields. Now, variety of high precision cutting, you can use this per se for drilling, milling kind of the operations of different kind of the materials, drilling of extremely small diameter holes with very high depth to diameter ratio, that is 25:1 aspect ratio you can obtain as high as 25:1 or even more, depends upon how efficiently you are able to remove the evaporated material from the hole or the cavity being machined. Please be careful, note it carefully that it is not only the drilling, you can cut or machine different kind of the different kinds of the cavities by having different movement or relative motion between the beam as well as the workpiece. Cutting of slots that are only about 25 micrometer wide is quite possible, easily done. To join or welding two pieces of the metal. Now, please note this electron beam welding is also very important area where lot of work has gone into. So, it is not only cutting or drilling or milling applications of electron beam machining, but rather electron beam has been effectively used for micro drilling purpose, micro welding purposes. So, to join or welding two pieces of metal to raise the temperature of material and relax any residual stresses. This is often done in conjunction with one of the other processes to reduce the number of steps needed to complete a part. So, electron beam drilling covers the areas like making of fine gas orifices in space nuclear reactor, hole in wire drawing die, cooling holes in turbine blades, metering holes in injector nozzle of diesel engine, etc. So, we will see, because especially say let me tell you that holes in wire drawing die, these wire drawing die are very hard material and it is really difficult to drill the very fine holes in wire drawing die by other processes, but this process, as we have seen, it can drill the very fine holes very efficiently in very hard material. So, we will see some of the applications of this particular process. Screens with about 10 million, this is million million, L is missing, holes per meter square through which soya beans are squeezed to produce tofu. We will show you the figure. Fiberizers for glass board production with about 50,000 holes in high temperature alloy is feasible by this particular process. Now, please see it carefully. This is the cross section, these are the holes and this is the cross section of the holes, this is the top surface of the holes. As you can see, very fine, these are the micron size holes which have been exaggerated to for our purposes to look into. We can easily see the shape and size of the holes drilled over here, and this is the cross section normal to this particular surface. If you take the cross section, then you will find this as the cross section of this one. Now, you can see here, this is the another case, this is shown figure 2 50,000 holes in high temperature alloy kind of the thing. Now, see clearly very fine cavity or very fine hole has been drilled over here, and you do not see the irregularities in the hole, and you have the very sharp edge of the hole being machined over here. You do not find the irregularities, and this is the cross section. Now, if you see it carefully, this particular cross section, the shape of this cross section is very similar to what I have already shown to you, and this is the cross section of the hole which has been machined in figure 2, and first one is for the purpose of soya beans. So, these are the two ones, and this has been taken from this particular reference. Now, for repairing purposes also you can use this particular process, very high cost component definitely, titanium material, high melting point, expensive, machining of aircraft engine parts. For that purpose you can use electron beam machining as well as electron beam micromachining. It can be used for to weld a plug of titanium into an incorrectly positioned hole in a large titanium casting. Suppose this is a large titanium casting and by mistake you have drilled a hole here, and which will damage the performance or spoil the performance or reduce the performance. What you can do, you will like to fill it up. For filling up, so that is what it says, to weld a plug of titanium into an incorrectly, this is the incorrectly positioned. So, you can weld it, and with the help of this particular process, to mill the plugged region to bore the required hole in the correct position, and you can mill it, you can drill the hole with this particular process in the right position. Cutting of apertures of some required form in self supporting thin files or wafers. Aperture can be cut of the required shape and size in the files or wafers, because files or wafers they are very thin, few hundred micron size or few tens of micron size, and it is really difficult to make any kind of features in these wafers. But such process like electron beam micromachining, laser beam micromachining, they can be, or even ion beam micromachining. When you are going for nano machining, you can use these processes if effectively and comfortably. Then you have the selective etching of deposited thin film on glass or ceramic substrate. Suppose you have deposited thin film over here like this is the thin film that has been deposited over the glass. Then you can machine this thin film with the help of this electron beam micromachining selectively. Wherever you want to etch it, deposit thin film that has been deposited, you can etch it or you can machine it in the area wherever you want and to whatever depth you want, that you have to control with the help of the energy input of the beam or energy input to every electron. Now, for making the photomask also this particular process has been used. As you can see here, repairing of defects in mask, certain mask has been prepared, and if you want to repair it, correct it, or something has gone wrong, you can use this particular process for repairing those masks. I have already discussed the application of mask when I was discussing abrasive jet micromachining. And mask for extremely ultraviolet and advanced phase shift with high selectivity and without damage to the underlying material, because mask is always there, and say suppose this is the main material or substrate and you prepare a mask and put it there. So, when you are repairing this mask, it should not damage this particular substrate or underlying material. But so this can be done with the help of electron beam micromachining, because you can control the depth up to which the beam is going easily. Then formerly a focused ion beam domain, earlier this was possible by focused ironing to repair or correct the defects in the mask. Now it can be done with the help of electron beam micromachining. So that is what is written here, that formerly a focused ion beam domain was there for correction, but now you can use electron beam micromachining also. Now became a focused electron beam domain. So it is under the focused electron beam domain. They have tried to give a new name rather than electron beam micromachining, they have given focused electron beam micromachining. So degradation of optical properties by gallium implantation and introduction of defects also can be done with the help of this particular process. Pattern generation for integrated circuit fabrication. In integrated circuit fabrication, you have the complicated patterns to be generated, and these bits of these pattern generated are few tens of microns or even smaller than microns. So you have to be careful while generating this pattern, but you can use this particular process for that purpose. Then you can see here applications remelting. Now surfaces are remelted to change the crystalline structure of the material, which affects its wear properties. See, this is one particular part, and this is the area which will have maximum wear compared to rest of the area, because this is discontinuity, it is coming in contact at high pressure with other material. So this wear out. So you want here the material to be deposited which has high or very high wear resistance. So the question is how to deposit it or how to melt it and deposit it. So this can be done with the help of the electron beam process. This can be done with and without additional substances, and it can be carried out on different materials. You can add the material, or what you can do, you can heat it and then cool it. So that hardening will take place, that is thermal hardening. You can do it, heat it and then cool it at the desired rate. Cooling rate will govern what is going to be the final hardness on this material which you have melted. So this material that you are melting may be the parent material of this particular part, or you can have the external material being deposited here. For depositing the external material, you may have to create some kind of cavity where you can deposit this particular material. So all this will be decided by the designer. Now very important thing, please see it carefully. This is the spinner used in glass fiber production, because you will find very fine glass fibers which are used in different applications, and you can see here 25,600 drilled holes with 0.55 millimeter diameter. So these are the drilled holes in number 25,600, and diameter of this is 550 micrometer, that is 0.55 millimeter diameter. Now here is the combustion chamber housing. 3,746 drilled holes are there in a certain area with 0.9 millimeter as the diameter. So you can see they are you may find they may look like a non-cylindrical because the surfaces are curved here, but if you see on other locations you will realize that they may be a circular holes also. This is the reference from where they have been taken. Now this is the mixer disc with 2,340 drilled holes, 0.9 millimeter as the diameter. So you can see over here, and please note it carefully that not necessary that they should be circular in nature all the time. As I have already mentioned, you can have even a non-circular holes with the help of electron beam micro drilling. Only requirement is you have to accurately control the relative motion between the workpiece being drilled and the electron beam. So you can have non-circular holes also at different locations. Now it is a ceramic material, not very clearly visible, but these are the holes, you can clearly see them. Here there are many holes in the ceramics which have been drilled. Ceramic contrast is not very good, but here very important thing you have to see that these are the angled holes, means they are not the straight sided hole like this. Here is a workpiece and the holes have been drilled at certain angle, and that you can clearly see over here as well as here, and it is really very difficult to drill the tapered hole or angled holes at different angles in the metallic parts or even in the non metallic parts. But if you can tilt the workpiece with reference to the electron beam, you can make this inclined hole or angled hole in any kind of the material, which is not feasible in various processes like electrochemical drilling. It can be done, but it requires lot of homework and lot of designing and optimization for that. So, but this is very simple, just if you can tilt the electron beam, you can get it. Now, you can see clearly high aspect ratio holes, this is the coin, and these are the, you can see the beauty of these holes, very uniform holes are there, and these are the top surface of the hole, this is the cross section of the hole, and thousands of such holes have been machined, and source is over here. Now, spinning cylinder, thickness of material 2 millimeter, left hand side this is the one, 45,000 holes of 400 micrometer have been machined in this particular sheet, and 80,000 holes in this particular area of 0.25, that is millimeter, that is 250 micron. Now, you can think of and see how many holes and how fast they can be drilled. In few minutes you can drill 80,000 holes. Now, this is the very important application, that is the turbine blade, you can clearly see over here, and turbine blade with holes for cooling air, because these turbine blades operate at very high temperature, 1100, 1200 degree centigrade, especially in aerospace industries, and they are very hard materials made of, and their cooling is very important, otherwise that turbine will fail, it may not be able to run at such a high temperature. So, you need the cooling holes, and these cooling holes are normally micro sized holes, but thousands and thousands in number, and to machine these holes in very hard materials like turbine blade material, normally industrialists were using earlier electrochemical micromachining process. Later they started using to some extent electric discharge micro drilling process, although thermal process, but it has some advantages, but so many disadvantages also. So, they have tried with the turbine blade using electron beam micromachining. Hole diameter is 200 micron, that is 0.2 millimeter, and thickness of the material is 1.7 millimeter, that is the thickness of this particular sheet through which they are going to drill the hole. You can clearly see this thickness, not the blade thickness, but the material with which this blade has been made is 1.7 millimeter, and you can see thousands of such holes are, these are just to show you, but there are thousands of such holes are there, and they may be straight or they may be inclined holes also, as we saw in the earlier sheet. Then this is the combustion chamber drill. Holes are, you can see here again, thickness of the material is 1.1 millimeter, hole diameter is 0.9 millimeter, that is 900 micron. Number of holes in this particular component are 3748, and they have been drilled with the help of electron beam micromachining, and processing time taken is 60 minutes. Now, this time is necessary because you have to index the workpiece continuously, and without indexing you will not get the hole location correct. So, very accurately you have to control the indexing, and really the time taken, this 60 minutes, large amount of time goes in indexing only, not really in drilling the holes. And this is the reference from where these pictures have been taken. Another application, as I mentioned you earlier also, is the electron beam welding application, where in this particular case you can see the repairing of the fan blades. Material is titanium aluminum 6 vanadium, power 5.25 kilowatt with 150 kilovolt, penetration depth is 3.5 millimeter and welding speed is 35 millimeter per second, which is very high in my opinion, and time taken is just 3.5 seconds. Then there is a stator wing ring which has been repaired or welded. Material is this stator, power is 8 kilowatt, 150 kilovolt, penetration depth is 10 millimeter and welding speed is again 30 millimeter per second. This is the weapon holder for tanks which are used in the war, and then you have rotor of a jet engine. Ring and disc are shown over here. These are the actual pictures of the rotor. Material Inconel 901 and power part 1 5.1 kilowatt power, penetration depth 5.3 millimeter and welding speed is larger than what we had earlier, that is 42 millimeter per second. And part 2 like this, here also the welding speed is, I do not know, it is written 4.2 millimeter per second, it has to be checked. Now, the question is, what are the advantages of electron beam micromachining? Very high drilling rates with small holes with large aspect ratio can be obtained. We have already seen high aspect ratio can be obtained, that is the depth over diameter of the hole drilled or depth and width of the cavity that has been machined, and machining rate or drilling rates are very high. We have already seen machined almost any material irrespective of their mechanical properties. We have already seen very hard material can be melted and vaporized easily, because temperature range in the machining zone is very high. So, as it applies no mechanical cutting force, work holding and fixturing cost is also very less, because we have seen that this is a thermal process. So, due to the melting and vaporization, material is being removed. So, minimal magnitude of mechanical force is being applied over there. So, fragile and brittle material can also be processed easily by this particular process, because in conventional machining processing of fragile material is really very difficult, because in many cases it damages or destroys the workpiece. The heat affected zone in EBM is rather less due to shorter pulses are used over there. In other thermal processes, this heat affected zone is thicker, just like EBMM process or laser beam micromachining process or plasma arc micromachining process. This heat affected zone is larger as compared to the electron beam micromachining. However, this process has certain limitations or disadvantages also. Capital cost of the equipment is definitely very high. Regular maintenance for any equipment using vacuum system is again also very high, because maintenance of the vacuum is very important. Otherwise, as we have seen already, that you will not get the desired qualities on the machined workpiece, and then significant amount of non-productive pump down period for attaining the desired vacuum. If your pump goes down or does not work properly, then lot of time you will be wasting as the non-productive time. Let us see what has been done in this particular lecture. Today we have discussed the effect of cutting speed on the characteristics of the machined cavity or the drilled hole. It to large extent depends upon the properties of the workpiece material, just like a thermal diffusivity, heat conductivity, etc. Then we also discussed the parameters which are affecting the width of the heat affected zone in electron beam micromachining as well as electron beam machining. Then I discussed the current density that you can calculate in case of electron beam micromachining, and then there was an equation which I gave you for calculating material removal rate in case of electron beam micromachining. Then we discussed how to calculate the value of W, which is the function of specific heat of the workpiece material in the form of solid, liquid, and then latent heat required for fusion as well as vaporization. After that, we discussed the characteristics of the hole drilled by this particular process, and we have seen that at the top or at the inlet of the hole you have a kind of curved larger diameter shape, while at the exit you have the narrow burr free exit hole compared to the top surface. Then we discussed various kinds of the applications of this particular process, which includes repairing of the certain parts which are very hard and have very high temperature of melting and vaporization. In those cases you can repair them by hardening the parent material itself or by adding the very hard material on the component. We have seen both the cases. Then we discussed many applications in drilling, and thousands of holes can be drilled in very short time. Many holes can be drilled, thousands of holes in some cases can be drilled in few seconds. After that, we discussed specific applications of this particular process, especially turbine blades, engines, stators. So, we saw that cooling holes, hundreds of cooling holes can be machined with this particular process in the turbine blades, which requires micro holes for cooling purposes. You can also have the holes at an angle rather than normal to the surface. You can drill these holes which are difficult by other processes, and then you can have such kind of the holes on the rotor also, stator as well as rotor. On both components you can have hole if required. Then I also mentioned about the electron beam micro welding application, certain examples were mentioned over there. And finally, I told you the merits or the advantages of electron beam micromachining process, electron beam micro welding process, as well as certain constraints or limitations of this particular process. And one of the constraints is that the cost of this particular equipment, maintenance cost is also very high. So, one has to be really very careful that while selecting this particular process, you should be able to justify that you really need electron beam micro welding process, for cannot be done by any other processes. Thank you very much.